It's Paul again, ready to get going with another video. This on the subject of the cross product. And while I swore I wasn't going to include anecdotes in these video recordings, I've got to tell you about the time that I was teaching a probability course, doing a fascinating problem in geometric probability. I needed the area of a parallelogram, and I announced that I was going to do it by calculating the cross product of the two vectors that span the parallelogram. One of my students immediately raised his hand and said, "I took Math 25. What's a cross product?" And the interesting thing is not that this fellow didn't know what a cross product was, it's that he was proud of the fact. Well, you won't have anything to be proud of because you're going to know what a cross product is. Let's get going. I'm assuming that you've looked through subsection 1.9 of the executive summary and perhaps listened to Kate's preview video, which does a much better job with that than I have time to do. I'm including the usual vector library so that we have access to functions that are now becoming fairly familiar, and I'm going to define the cross product. I'm going to define it with a function whose name begins and ends with a % sign and has an x in the middle. This is a function of two vectors, and here's how you work it out. For the first component, you don't want to use a 1. So you use v2 times w3 minus v3 times w2. For the second component, you mustn't include a 2, but you want to keep the numbers in cyclic order, 3, 1, 2. So it's v3 times w1 minus v1 times w3. And for the third component, which is actually the easiest, you want the order 3, 1, 2. So you have v1 w2 minus v2 w1. The hardest part of this operation is remembering where the minus sign goes. In order to illustrate all the important properties of the cross product, I'm going to need 3 vectors. So let's define them. Any 3 vectors will do. Remember, you can't prove anything by doing examples in or R, but looking at one illustration gets you on the right track. First property. This is an anti-commutative operation. If I take the cross product of u and v and the cross product of v and u, I get 2 vectors, one of which is the inverse of another. And since the only number that changes its sign when you take its, I said that wrong. The only number that stays the same when you slap a minus sign onto it is 0. If you take the cross product of a vector with itself, you're guaranteed to get 0. Like the dot product, the cross product is linear in either factor, or, if you prefer, it obeys a distributive law. So, for example, if I take the cross product of u with v plus w, or alternatively, add together the cross product u cross v and u cross w, I get the same answer in either case. The cross product of standard basis vectors is very easy. If I take the cross product of the first and second standard basis vectors, I get the third standard basis vector. If I'd done that in the opposite order, of course, I would have got minus the third standard basis vector. Now here's a really remarkable result. We've got both dot and cross products. One thing I can do is to take the cross product of v and w and then take the dot product with u. Or I can switch the parentheses and the operations, take the cross product of u and v, and form the dot product with w, and remarkably, I get the same answer in either case. Oh dear. Can I get back to where I was? Okay, I swore I was never going to do one of these recordings twice, so I've wasted half a minute of your time, but who cares? So why is this triple product of u, v, and w the same no matter where I put the parentheses? The answer is it's exactly the same thing as the determinant of the matrix whose three columns are u, v, and w, also minus 11. In physics especially, you often have occasion to take the cross product of two vectors and then take the cross product of that cross product with a third vector. There's a simple rule for this that has only one thing that's hard to remember. It's fairly easy to remember that the result involves one factor which is something times u and one factor which is something times v. Those are the two vectors that are in parentheses. And the rule you've got to remember is the vector in the middle gets the plus sign. That works whether the parentheses are around the first two vectors or around the last two vectors. So you take the two vectors in parentheses, v and u, you multiply each of them by the dot product of the two remaining vectors, and then you slap the plus sign on the vector in the middle, and behold, you get the same answer in either case. This is an interesting example of an operation that's not associative. You can take the cross product of three vectors, but the order makes a difference. If I put the parentheses around the second and third vectors, I get a somewhat different number. It turns out there is a more complicated version of associativity that takes over in this case. It's known as the Jacobi identity, and I believe the proof is one of the homework problems. What the Jacobi identity says is that if you do this in the three possible ways and add them all together, you get 0. What about the length of a cross product? Well, we can take the length of a cross product, we can take the length of a dot product of u and v, and we can take the product of the lengths, and the interesting result is that the length of the cross product is equal to the product of the lengths minus the square of the length of the dot product. And this will turn out to be equivalent to the well-known trigonometric identity that sine squared theta is equal to 1 minus cosine squared theta. It's even possible to take the dot product of two cross products. I need for this 4 vectors, so I've added a vector x to my compendium of vectors u, v, and w. And what I'm going to do is, first I'm going to take the cross product of u and v, then I'm going to take the cross product of w and x, and then I'm going to take the dot product of the two. And it turns out the result is the same as what I get if I take the dot product of the first two and the dot product of the last two, multiply them together, and subtract off the dot product of the outside ones multiplied by the dot product of the inside ones, again getting 66. Proof of this makes a nice problem. Now let's think about this geometrically. As you've learned, if you've ever taken a physics course, the cross product of two vectors is perpendicular to the plane that they span, and the way we prove this algebraically is by taking the dot product of each of the two vectors u and v with their cross product. In both cases I get 0, proving that both these vectors are perpendicular to their cross product. Remember, the dot product is equal to the product of the lengths times the cosine of the angle between the two vectors. The length of the cross product is the product of the length of the two vectors multiplied by the sine of the angle between them. as I can verify in a specific case by taking the length of the cross product, and alternatively by taking the product of the lengths and multiplying it by the sine of the angle between the two vectors. Geometrically, what this means is the length of a cross product is the area of the parallelogram spanned by u and v, which is why I was using it in that probability course that I alluded to at the start of this narration. And here's a cute proof of that result. We got a parallelogram. Let's make a unit vector perpendicular to that. Well, I can make a vector perpendicular to the parallelogram by taking the cross product of the two vectors u and v that span it, but that's not necessarily a unit vector. To make it a unit vector, I divide it by its length. Now, since I can't draw good graphs in R in 3 dimensions, you'll have to do some visualizing. I've got a parallelogram, and I've got a vector that's perpendicular to that parallelogram. I have converted the parallelogram into a prism. Its height is 1, and therefore its volume, which is its base times its height, is equal to its base area. We can calculate that by taking the dot product of n with u cross v. But since the height is 1, the volume of the prism must be equal to its base area, which proves that the base area is equal to the magnitude of u cross v. Frequently, you want to check whether 3 vectors in R3 are what's called linearly dependent or linearly independent. If they're linearly dependent, they all lie in the same plane. If they're linearly independent, then I can make any vector in R3 by summing up appropriate multiples of them. Or equivalently, they form a 3-dimensional solid, a parallelepiped, whose volume is not 0. The volume is given by the triple product of these 3 vectors, u, v, and w. And for the 3 vectors I've chosen, this triple product is minus 11, which means that these 3 vectors are independent of one another. You've all learned the handy-dandy rule for inverting a 2x2 matrix. There's only one other size of matrix for which there's a simple inversion rule. That's a 3x3 matrix, and let me now introduce it to you. We've got our 3 vectors, u, v, and w. Let's bind them together into a matrix and try to figure out its inverse. Here's how. Look at the last 2 columns, v and w. If I take the cross product of those vectors, it's orthogonal to the last 2 columns. And if I view that as a row vector, when it acts on the last 2 columns, it's going to give 0. What's it going to do when it acts on the first column? Well, when it acts on the first column, we're effectively calculating u dot the cross product of v and w, and we get the determinant, which, as you've seen on several occasions, is equal to minus 11. Now, R is happy to treat the cross product of v and w as a 1x3 matrix if I put it on the left of the matrix M. So when I do this matrix multiplication of a 1x3 matrix by a 3x3 matrix, I'm going to get minus 11 when I multiply by the first column, which is u, and of course I'm going to get 0 for the other 2 columns. Now let's get really clever. Let's do the same thing with v cross w, w cross u, and u cross v. The same argument works in every case, and I can stack up these 3 rows to make a matrix A. When I multiply A by my original matrix M, I'm always going to get 2 zeros, and I am going to get a minus 11 on the diagonal. That's almost but not quite the identity matrix. All I would have to do in order to get the identity matrix is divide by the determinant of M minus 11. So if I take the matrix A and divide by the determinant of M, I get the inverse matrix, and it's easy to check that on multiplication I have the identity matrix. So this is probably the simplest way of writing down the matrix of writing down the inverse of a 3 by 3 matrix, and that ends this narrated R script.